class, we talk a lot about heat transfer, and we know that heat can do a lot of neat things for us. It can generate work, it can heat a house, it can cool a house, but how do we get heat to go where it needs to go? And the answer to that might be a heat exchanger. We're going to talk about two types of heat exchangers right now, a direct contact heat exchanger and an indirect contact heat exchanger. In a direct contact heat exchanger, you have a hot stream and a cold stream coming in, and they mix together to form a single stream at some temperature in the middle. An example of where you might find this is in your shower. You've got a hot stream and a cold stream, and you can change the mass flow rates of each to get a temperature to your liking. The other type of heat exchanger that you may see is an indirect contact heat exchanger. So you have, what you see here is a simple tube and shell heat exchanger. You've got a cold fluid flowing through the tube and a hot fluid flowing through the shell, or vice versa. They're at a different temperature. And they don't exchange heat by directly mixing, but they exchange heat through a physical medium. An example of where you might find this is in a steam cycle. So this is used to generate power. And when it's used in this manner, it's called a closed feed water heater. So you'll have a hot stream coming from a turbine, and you've got a cold stream going through a tube or a series of tubes, and that'll be your cold stream. And your steam will condense over those cooling coils, and it'll condense as a liquid out the bottom, and what's going through the tube will be heated up. So that's one way to move heat around within a steam cycle. So now let's talk about how we analyze each of those systems. Let's talk about the direct contact heat exchanger first, and then we'll analyze the indirect contact heat exchanger. So it's an open system because you've got mass flowing in and mass flowing out. So we've got two equations that we know how to use right now. We've got our conservation of mass and our conservation of energy. If we apply our conservation of mass to that direct contact heat exchanger, you see that we've got dm dt equals the sum of the mass flow rates coming in minus the sum of the mass flow rates going out. If you operate at steady state, that dm dt goes away, and so you're left with the sum of the m dots coming in equals the sum of the m dots going out. So what that boils down to here is m dot 1 plus m dot 2 is equal to m dot 3. Now let's look at the indirect contact heat exchanger. Now when we apply our conservation of mass here, you need to be cognizant of the fact that mass doesn't actually cross that physical boundary. So you apply your conservation of mass to the fluid flowing through the tube, then you apply it to the fluid flowing through the shell. So your mass flow rate for the tube, it's m dot 3 is equal to m dot 4. And then if you apply it to the shell, m dot 1 is equal to m dot 2. So now we've got our conservation of mass taken care of, and we're ready to apply our conservation of energy. So here's our conservation of energy, dE dt equals q dot minus w dot plus the sum of a whole bunch of stuff coming in minus the sum of a whole bunch of stuff going out. Now let's look at the things that can go away in that big long equation. We're operating at steady state, so that dE dt goes away. And for a heat exchanger, the only heat that you want to be exchanged is between the cold and the hot streams. And so as a unit, that entire unit is insulated. So if you draw your control volume around that entire unit, the heat transfer is going to be negligible for that process. So that Q dot drops away. Now let's look at the work. There's no work generated, no work required. There's flow work, which is required to push that fluid in or remove it from the system, but that's taken into account with the enthalpy term. So the W dot goes away. And there's no changes or negligible changes in kinetic and potential energy, so those go away, and all you're left with is the sum of the m dot h's going in equals the sum of the m dot h's going out. And that's applicable for both of those types of heat exchangers. So let's look at the direct contact heat exchanger. When we apply our conservation of energy, we get m dot 1 h1 plus m dot 2 h2 equals m dot 3 h3. And I can simplify that a little bit if I want to. I can bring my conservation of mass in and define m dot 3 in terms of m dot 1 and m dot 2 if I wanted to, and simplify things a bit. Now let's look at our indirect contact heat exchanger. So it's still the sum of the m dot h's coming in is equal to the sum of the m dot h's going out. And I've got two inlets and two outlets. So I've got the m dot h's coming in equals the sum of the m dot h's going out. So I've got fluid going in at state 1 and state 3, and it's going out at state 2 and state 4. And then I can come in and I can apply my conservation of mass, And because m dot 1 and m dot 2 are equal to one another, and m dot 3 and m dot 4 are equal to one another, I can replace the m dot 2s with m dot 1s, the m dot 4s with m dot 3s, and I can simplify my equation quite a bit. Another word about the indirect contact heat exchanger. While if I draw my control volume around the entire unit, I don't have any heat transfer, I might be interested in knowing what the heat transfer rate is between those two streams. So in order to figure that out, I need to draw my control volume so that I do have heat transfer crossing the boundary. So let's draw our control volume around the tube. So the heat transfer rate for the tube, if I apply my conservation of energy, everything is the same except now I have a heat transfer term. So it's going to be Q dot for the tube is equal to the sum of the mass flow, the sum of the m dot h's coming out, minus the sum of the m dot h's going in. So it would boil down to m dot 3 times h4 minus h3. Now I can look at the shell. So if I draw my control volume just around the shell, it'll be Q dot for the shell equals the sum of the m dot h's coming out minus the sum of the m dot h's going in, which would be m dot 1 times h2 minus h1. And because the only heat being exchanged is between those two fluids, the heat transfer rate that you calculate for the tube should be the same magnitude as the heat transfer rate that you calculate for the shell, but it should be the negative. All right, well, I hope that was helpful and thank you for watching.